Imagine sitting inside a train as it begins to accelerate. At first, everything feels normal. Then, at around 160 kilometers per hour, something incredible happens. The wheels quietly retract, and the train lifts itself off the track. From that moment on, it isn't rolling anymore. It's floating on a magnetic field. Within minutes, it races past 500 kilometers per hour, eventually reaching a record-breaking 603 kilometers per hour during testing. This is Japan's SCMaglev, one of the most ambitious transportation projects ever attempted. But creating the world's fastest train wasn't just about building a faster railway. It became one of the most challenging engineering projects in modern history, taking more than 60 years of research, billions of dollars in investment, and decades of construction. The story began in 1964 when Japan introduced the world's first Shinkansen, better known as the Bullet Train. It revolutionized rail travel by connecting major cities at speeds never seen before. The system became famous for its incredible safety, reliability, and punctuality. Over the following decades, millions of passengers depended on it every year. Eventually, however, one major problem appeared. The busy route connecting Tokyo, Nagoya, and Osaka was reaching its maximum capacity. More trains couldn't simply be added because the railway was already operating near its limit. Engineers realized that upgrading the existing line wouldn't be enough. Japan needed an entirely new transportation system. Instead of improving conventional rail, researchers explored an idea that sounded almost impossible: a train that never touches the track. This concept became magnetic levitation, or Maglev. Instead of steel wheels creating friction against rails, powerful superconducting magnets lift the train about 10 centimeters above the guideway. Without wheel-to-rail contact, almost all friction disappears, allowing the train to travel at extraordinary speeds while producing a remarkably smooth ride. Research into this technology began in the early 1960s, but proving that it could work reliably required decades of testing. Small experimental tracks gradually evolved into larger testing facilities. Engineers spent years studying everything from passenger comfort to magnetic stability and emergency braking systems. Their efforts paid off. In 2015, Japan's test train achieved an incredible 603 kilometers per hour, setting the world record for the fastest rail vehicle ever built. Building the train was only half the challenge. Building a railway for it proved even more difficult. The direct route between Tokyo and Nagoya crosses Japan's rugged mountain ranges. Going around them would make the journey much longer, so engineers made a bold decision: tunnel straight through the mountains. Nearly 86% of the new railway would run underground. That meant excavating around 246 kilometers of tunnel, making it one of the largest tunneling projects ever attempted anywhere in the world. The mountains quickly reminded engineers that nature doesn't always cooperate. Some tunnels pass beneath mountains over 1,400 meters high. Workers encountered fractured rock, underground rivers, unstable fault zones, and enormous rock pressure capable of deforming tunnel walls. In some locations, giant tunnel boring machines advanced efficiently. In others, the geology forced engineers to abandon those machines entirely and switch to slower drilling and blasting methods. Progress slowed dramatically, but construction continued. Once the tunnels were finished, another extraordinary challenge began. Unlike a conventional railway, the SCMaglev doesn't carry its own propulsion motors. Instead, the motor is built into the track itself. Hundreds of thousands of electromagnetic coils are installed along both sides of the guideway. These coils provide propulsion, guidance, and levitation simultaneously. Installing them required incredible precision. Every section of the guideway had to be aligned with millimeter-level accuracy using advanced laser surveying equipment. Even tiny errors could affect performance when trains travel at over 500 kilometers per hour. Inside the train, equally remarkable engineering is hidden from passengers. Each vehicle contains superconducting magnets cooled with liquid helium to temperatures close to absolute zero, around minus 269 degrees Celsius. At these temperatures, electrical resistance nearly disappears, allowing extremely powerful magnetic fields to be generated efficiently. Below 160 kilometers per hour, the train rolls on rubber tires. Once sufficient speed is reached, those tires retract automatically, and the train begins floating silently above the guideway. Safety remained one of Japan's highest priorities throughout development. Traveling at such extreme speeds creates unique engineering challenges. Entering a tunnel at 500 kilometers per hour generates a powerful pressure wave. To solve this, engineers spent years refining the train's long aerodynamic nose using wind tunnel testing, reducing both noise and sudden pressure changes for passengers. Because Japan experiences frequent earthquakes, the railway also includes thousands of seismic monitoring sensors. If an earthquake is detected, electricity is immediately cut and trains automatically begin emergency braking before the strongest seismic waves arrive. The U-shaped guideway also helps prevent derailment even during severe ground movement. Engineering wasn't the only obstacle. Construction faced environmental concerns, especially in Shizuoka Prefecture, where local officials worried that tunneling could reduce groundwater supplies feeding nearby rivers. Years of negotiations followed before engineers redesigned water management systems to protect local water resources. These delays pushed the opening date back several years while construction costs continued climbing. What was originally estimated at around $9 billion eventually grew to more than $70 billion, making the project one of the most expensive railway developments in history. Even today, thousands of workers continue building tunnels, stations, bridges, and guideways across central Japan. When completed, the SCMaglev is expected to reduce travel time between Tokyo and Nagoya to only 40 minutes, nearly cutting today's journey in half. It will also provide additional capacity for one of the busiest transportation corridors on Earth while offering an alternative route during major natural disasters. Whether the SCMaglev becomes the global standard for future railways or remains one of history's greatest engineering achievements, it has already demonstrated what's possible when decades of scientific research meet extraordinary determination. More than 60 years after the idea was first imagined, Japan is proving that the future of transportation doesn't always run on rails. Sometimes it floats above them.